So this QOD video is going to be about two topics, the periodic table, which we've talked some about already in class, and then also the concept of atomic weights, which actually flows from the periodic table. So these slides are somewhat adapted from your book, although I've made some adjustments to them. So the periodic table is really just a systematic listing of the elements, and they are arranged in ascending order of atomic number. That is how many protons they have in their nucleus. And so you can see starts with 1, 2, 3, 4, 5, 6, etc. It's always in ascending order of atomic number. We have talked about this already in class, that the rows in this chart are called periods, and that the columns are called groups. And some of those groups have special names, and those are some things that we have talked about. And that elements in the same group, this is something we actually haven't talked about yet, and I'm going to show you some videos to demonstrate this for you. Elements in the same group have similar chemical properties. So just to go over what's here, the horizontal rows are periods, the vertical columns are groups. The elements are arranged in ascending order of atomic number. And then there's this stair step that we will talk about a little bit later on. One other classification that's useful to know about the periodic tables is what are known as the main group elements versus the transition elements. And so these elements in groups 1 and 2, or 1A and 2A, and then 13 through 18, or 3A through 8A, they are known as the main group elements. And then these elements in groups 3 through 12 are known as the transition metals. We will talk about this in much more detail, but it's just useful to know that the taller groups, the taller columns, groups 1, if we're looking at the A designation, groups 1, 2, 3, 4, 5, 6, 7, 8A are called the main group elements. And then this set here in the middle is called the transition metals. So how did we get to this idea of having groups and periods? Well, this came from the observation nearly 200 years ago now, that if you arrange these things in ascending order of atomic number, you would start to see repeating patterns, so that every time you had a non-reactive gas, then that would be followed by a soft reactive metal. Then further up the list, there would be another non-reactive gas followed by a soft reactive metal, etc. So when you look at the chemical properties of the elements, if you arrange them in order of ascending atomic number, you'll see that you see repeating patterns. We've talked about the names of some of the groups already. Groups 1, 2, 7, and 8. You do not need to know that the group 6A is called the alkogens. Nobody ever uses that term. But group 1, 2, and then 7A, 8A, or 17, 18 under the other numbering system are known respectively as the alkali metals, the alkaline earth metals, the halogens, and the noble gases. Okay, let me actually just stop this for a second and talk and show you some examples of how things that are in the same group have similar reactivity. So this video is actually, I've turned the sound off, and so I'll kind of narrate it for you. This is the alkali metals. All alkali metals will react with water to form the metal hydroxide plus hydrogen gas. And so we start by adding lithium to water. And so when lithium is added to water, you will see that it fizzes. Hydrogen gas is being produced here. That's kind of the smoke or vapor you're seeing. And it fizzes. If I add sodium, which is now down 1 from lithium in the alkali metals, you'll see that the same reaction is occurring, and it is occurring more vigorously. That's just the equation for the reaction that's occurring. That's less of a concern for us right now, but just to see that it happens. And when you go from lithium, it becomes more vigorous. Now we're going to look at potassium, which is the next element down. Now you can see that actually it catches fire. So the reaction is so vigorous that the hydrogen that's being generated starts burning. That causes the potassium basically to break in half. Rubidium, which is down below potassium now, the minute it hits the water, it just kind of explodes. There's another look at it. And then finally, we're going to see the most, as the narrator of this calls it, the most terrifying of all, which is cesium. And when cesium gets added to the water, it explodes and the whole container. And so that's an example of the fact that the alkali metals all have similar properties. They're all soft metals that react with water, and go down the group, their reaction becomes more vigorous, and that's something you might want to note because that's something that might appear on a QOD, for example. The flip side is to look at the reaction of the halogens, that is group 7A or group 17 with aluminum metal. And so we're going to start at the bottom of the halogen column, which is iodine. So I'll turn this on. So some iodine and some aluminum are going to be mixed here. So they're put together and they're mixed, and you'll see that a reaction is starting to occur. It takes a little while for this to get going, but eventually it's going to catch fire. Actually, you can see right there that it's catching fire. So the reaction of aluminum with iodine to form aluminum iodide, it starts out kind of slowly, and then after a period of time, it catches fire, and then eventually the fire goes out. Here is bromine and aluminum. Now you're going to see here that it actually becomes more vigorous, that the bromine that the aluminum in the bromine is going to catch fire really quickly. And as soon as it catches fire, it's just going to start burning very vigorously, much more so than we saw with the burning of the iodine. So whereas the alkali metals get more reactive as you go down the group, so if you go from lithium to sodium to potassium to rubidium to cesium, they become more reactive. For the halogens, it's the reverse. They become more reactive as you go up the group. Here's putting foil into chlorine gas, and it will just very quickly catch fire and start burning really out of control. So iodine was the least reactive. Coming up to bromine is more reactive. Now we're looking at chlorine, which is more reactive still. And then finally, you're going to see what happens when you put fluorine and aluminum together. It is so reactive that it's just over almost instantaneously. Boom. Okay, so all that to say that, stop that. All that to say that as that elements in the same group have similar reactivities, and there are trends in reactivity, so that as we went down the alkali metals, they became more reactive, going from lithium down to cesium. As we looked at the halogens reacting with aluminum, they became more reactive as you went up, iodine to bromine to chlorine to fluorine. Well, in addition to thinking about groups and columns and transition metals versus main group elements, we can also divvy up the periodic table according to whether a thing is a metal or a non-metal, and that's really pretty much determined by this stair step that is in right here. So everything to the upper right of the stair step, which is indicated here in green, as well as hydrogen, which is over here, is considered a non-metal. So those are the non-metals. There's a small group and set of elements that are known as metalloids, which inhabit the sort of area, the region of the stair step itself: boron, silicon, germanium, arsenic, antimony, tellurium. When I was learning chemistry, when I was your age, these were referred to as the semiconductors. They're generally now referred to as the metalloids. They have properties that are in between those of metals and nonmetals. And then anything down to the southeast or southwest of the stair step is going to be a metal. So the vast majority of metals, the vast majority of elements on the periodic table are metals. They have common properties. They tend to be solid, lustrous, malleable, conductors of electricity. The nonmetals are really not characterized by any specific properties that they share in common, other than their properties are not like the metals. And then the metalloids tend to be somewhere in between. Now, let's just switch off and start talking about something else, which is the concept of atomic weight. And here I've taken, not from this periodic table, but from another periodic table, broken out the little square that belongs to iron. So Fe is the symbol, iron is the name. It's element 26, just like you can see here. Most periodic tables also give what's called the atomic weight of the element. And here iron is given as 55.845. Now, the question that may arise in your mind about that number, that atomic weight, 55.845, hopefully at some point, if you thought about it long enough, this may arise, is where does that number come from? What does 55.845 represent? Is that the mass of a particular isotope of iron? And shouldn't the masses of isotopes of iron have whole numbers, like we've talked about iron 56 or carbon 12, carbon 13, et cetera? Shouldn't these things have whole numbers? Where's that 55.845 coming from? Well, a couple things about this. First of all, that's called the atomic weight, or the average mass of an iron atom. So let's talk about a couple things. As it turns out, the actual masses of the various isotopes of various elements are not whole numbers, and we won't go into this in detail as to why, but they're usually slightly more or slightly less than the actual name of the isotope. So iron 56 is called iron 56 because it has a total of 56 protons plus neutrons, but its actual mass is 55.9349 AMU. Very close to 56, but not exactly 56. Similarly, uranium-238, which is the most abundant isotope of uranium, it has a mass of 238.0508 atomic mass units. So that's one thing. The mass of these isotopes are not actually exactly whole numbers. But the other thing is that for most elements, there's more than one isotope that occurs in nature. And so the average mass of a given element, that is its atomic weight, is actually a weighted average of the masses of the various isotopes and their abundances. This is the way your book would say it. Because in the real world, we use large amounts of atoms and molecules, we use average masses in calculation. And so since when we weigh out some carbon, we're weighing out billions of billions of billions of atoms, then it makes sense to actually not think about do I only have one isotope of this carbon. I've got some naturally occurring mixture of all the isotopes of carbon, and I need to account for that by using the average weight of those. And so the average mass, or what we also call the molecular weight, is calculated from the various isotopes of an element, weighted by their relative abundances. So let's take a very, very simplified look at this. And I'm going to talk about, imagine that there is some new metal discovered called jonesium. And jonesium has two isotopes that occur in nature, and their natural abundance is exactly 50-50. That is, every other isotope of jonesium is isotope A. So exactly half of the isotopes of jonesium are isotope A, which has a mass of exactly 55 AMU. And the other half, exactly, of all the isotopes of jonesium are isotope B, which has a mass of 56.0 AMU. So what's the average mass of jonesium? Well, that should be pretty straightforward. The average mass of a jonesium atom would be 55.5 AMU. That's just the average of those two numbers because they occur in nature in a 50-50 ratio. So if you were weighing out billions and billions and billions of jonesium atoms, you would assume that the average mass, since you're going to get a 50-50 mixture of these two isotopes, and so you would treat the mass of an atom as if it were the average mass of those two isotopes. Well, most elements, as we've said before, don't have isotopic masses, which are exactly whole numbers, and their abundances in nature are not exactly 50-50. And so a great example of this is chlorine. Chlorine has two isotopes that occur in nature, but their natural abundance is not 50-50. The lighter isotope is chlorine-35, whose mass is not exactly 35, but very close, 34.9689. Its natural abundance is 75.76. That is 75.76% of all the chlorine atoms in the universe are chlorine-35. And you would assume that if you had a sample of chlorine, which contains billions of billions of billions of atoms, that you're going to get an even you're going to get that distribution of chlorine atoms in which 75% of them are chlorine 35 and the other 24.24% are chlorine 37, which has a mass of 36.9659. So the natural abundance of these are not 50-50, so I can't just take the average of those two numbers, 34.96 and 36.96. I have to do what's called a weighted average. And the way I do a weighted average is, again, I've got these two isotopes. I know their masses. I know their abundances. I'm going to take each one and multiply the atomic mass of that isotope by its abundance. And now I'm going from treating these as percentages is just treating them as fractions. So 34.9689, which is the mass of chlorine 35, times its natural abundance, 0.7576, gives me this number, 26.49. If I take chlorine 37 and multiply it by its mass by its natural abundance, I get 8.96. It's actually 8.961, but that's going to drop off when we add these together. When I add those two numbers together, I get 35.45, which is the mass of chlorine, the atomic weight of chlorine that's given on the periodic table. Does this make sense? Yeah, it makes sense. There are two isotopes, chlorine 37 and chlorine 35. If they occurred in nature in a 1-to-1 ratio, you would expect their average to be right around 36. But because there's 3 times as much chlorine 35 as there is chlorine 37, you would expect that weighted average to be closer to 35 than it is to 37. And it is. It is 35.45, which is much closer to 35 than it is to 37. How do we actually figure out what the masses of these isotopes are and what their abundance is? We use what's called a mass spectrometer. And what that does, I'm not going to get too deeply into this, but it takes chlorine atoms and ionizes them and then shoots them in a beam. And then these magnets cause the beam to turn. But they're going to turn more if they're lighter, and they're going to turn less if they're heavier. So the chlorine 35 is going to be turned more sharply than the chlorine 37. And then it's going to strike a detector, and it's going to register what the masses of these things are and how often they're striking. And so here's a mass spec of chlorine in which the y-axis is the signal intensity, and the x-axis is the atomic mass. You can see that this says 35. If you have a very sensitive instrument, it'll actually tell you that it's 35.96, I'm sorry, 34.96, and that this 37 is actually 36.96. But also the intensity, the area under the curve tells you what their relative abundances are, and that's where we get the 75.76% and the 24.24%. Okay, there'll be a QOD on this in the morning, and so I've looked for the assignment. Well, you've seen the assignment because you've got to this video, but look at some of the suggested problems that might turn up on the QOD, and we'll talk to you later. Bye-bye.